Hey guys, BuildZoid here, and today we're going to be taking a look at the Power Bridge mod that I've done to my RTX 3060 Ti. And before we get into this, I would like to point out that the idea of a Power Bridge mod isn't my idea. I just stole it from Asus. See? This is the GTX 670 DirectCU 2 Mini. And on this card, like that, they basically just have like a copper plate that connects the vCore of the, like the output of the vCore VRM to the GPU core directly. Now, obviously, that card still has like a vCore power plane in the PCB itself, but the idea behind doing this is that you can get a lot more like cross-section of copper, and therefore a lower resistance connection between the core and the VRM without having to have a like crazy high layer count PCB. And, this is potentially cheaper than just having a bunch of extra layers, and it reduces the power loss in the power plane, which should make the power plane run a little bit cooler, which by extension could make the VRM run a little bit cooler. Also, the GPU core may be a little bit cooler. It can also potentially help with voltage regulation, depending, like, technically the voltage controller compensates for the power losses in the power plane. Like, it does that. But you can have benefits from just not having huge amounts of power losses in the power plane to begin with. So, yeah, not my idea. I stole it from Asus, and I did it, much uglier. I made it much, much uglier. It doesn't look that bad until you zoom in. So, yeah, anyway. Let's talk about it. Now, this is not the best Power Bridge mod I've ever done. In fact, the most effective Power Bridge I've ever done is the one I have on that GTX 1080 FTW that I resurrected. And actually, that modification needs to get redone because there's some structural integrity concerns with it because I very lazily soldered the Power Bridge to a bunch of multi-layer ceramics, and multi-layer ceramics are many things, but structurally sound is not one of them. They really aren't meant to have like a bunch of like physical stress applied to them. And so what I did was like I knew from the get-go that it was a bad idea. I really miscalculated just how bad. So yeah, I've already had to face the consequences of my poor decision making on with that card, and so that'll have to get fixed eventually. Like the card still runs. It's just that it needs some adjustments because the current condition it's in is not a little bit suboptimal. Anyway, this on the other hand is much less of an issue because the power bridge isn't as long as they're like a lot of the things that are wrong with the 1080 configuration. Though electrically that one works way better. It's just physically very fragile. This one is not physically fragile. It's just really ugly. So anyway, and electrically not very effective. It's nowhere near as effective as the one on the 1080. Like the one on the 1080 made such a difference, but this one doesn't. And it's obvious why. This is way less cross section. And there's just a lot less copper in this one than there is on the 1080. But unlike on the 1080, I have a lot more measurements for this one. So let's take a look at those. Yeah, the first thing that's sort of cool with the 3060 Ti. So basically, I decided to measure the power losses for a variety of different, so actually, no, I guess I should start with the test methodology. It's always so, like, I've a lot of the time I feel like I make too many assumptions that people will know what is going on with the things that I am doing. So let's start. So, first of all, the core voltage is manually controlled. I have it locked at 1.07.3 volts for these tests because that's what the volt mods are for. And there's already a video up on the channel about the volt mods. So anyway, so there's a volt mod, and that handles that locks the core voltage to 1.073 volts. This is important because if you don't lock the core voltage, the NVIDIA drivers will just pull it up, pull it down, it'll never stay constant, and you can't get a proper measurement if the voltage isn't constant because, to make sure that the load is relatively constant, I actually had the card running on a frozen frame in 3D Mark Firestrike in roughly the same spot every single time. And so that allows to get a pretty accurate measurement, because the thing is my card doesn't have a power limit, so the power draw will actually it doesn't have a power limit. It has a really, really, really high power limit relative to what's normal for a 3060 Ti, and so the power draw is free to go up and down a lot, and so the card, the average power, that would obviously affect the measurements as well. So you have to be sort of doing the same exact thing the same way every time when taking these measurements, but that's all accounted for. Anyway, I took measurements for different inductors on this card because, like, looking at the card, right, it became sort of like one. Well, actually, I should have included the top photo of the card as well. But anyway, so looking at the card, you can very clearly see that we have like this big polygon over here, and this polygon is actually all V-core, right? And then there's this like strip over here that heads towards the GPU core, and that's more V-core. And then behind the core, you have just a total mess, and we're not going to get into that right now. But anyway, so you can see like you have this V-core polygon, and then it gets rudely interrupted by whatever these like data, like, yeah, this is probably some kind of data. I assume this is current monitoring stuff. So, yeah, NVIDIA's crazy obsession with input power management is leading to worse power plane designs because you've got to run these silly traces to the like current monitoring chips. Like, really, look at where these go. These go like all the way around the card, and I think they run through like here. And then I merged this into the image layer, so that's not going away. And then it goes all the way, and it's just like. And I'm 99% certain that on the other side, actually, it might be for fan control. Fans are unimportant too. Anyway, actually, no, please, no, fan control is important, but yeah, anyway, so you can sort of see like how we have this like, nice big blob of V-core and more V-core over here, and then there's like this cut into that. But compared to what you have on the other end of the card, it's actually not that bad because on the other end of the card, we've got all of the PCIe. And so there's just nothing, right? Like you've got like a V-core polygon sort of in this area. Actually, I'm not even sure that's V-core. I'm pretty sure that might be ground looking at it. Yeah, that's probably a ground polygon by the looks of things. So, yeah, like you've got all of this stuff over here. And then you've just got PCIe traces. And so one of the things I was wondering about is sort of like how, like the VRM is obviously like horizontal to the GPU core, but one of the things I was wondering about is like, okay, so looking at the way this power plane seems to be arranged, can we actually measure that most of the current goes like this? Because it visually, like, and if you look on the other side of the card, it actually like implies the same kind of behavior, because actually you might be thinking, is this V-core? That's not V-core. That's, I think, the 1.8 volt rail or the PEX rail, something like that. There's like a minor rail that runs through that area. Anyway, so, looking at this VRM layout, I was wondering, okay, can I measure that the current actually does something like that? And answer to that question is yes, I can. Because I took a measurement of the top inductor, middle inductor, and bottom inductor, which means I took a measurement of this inductor, and this inductor. Yes, that one's still part of V-core. And you can see that, so, obviously this is top, this is bottom, like middle, bottom, and all of these measurements are relative to the PCIe slot bracket, like the rear I/O bracket. And the reason why I'm taking it against the rear I/O bracket is because you can just chuck your ground probe of the multimeter through that, and it's super convenient. Not accurate, but very convenient. So that is something to actually, like, the problem with this is it's not going to like drastically cause massive inaccuracy issues. It's just that it doesn't, like, you'll notice that I have like, so the orange wires are obviously like V-core connections and the black wires are obviously ground connections. Well, if I'm always checking my ground connection, if I'm always taking my voltage measurements relative to the rear I/O bracket, I can't actually measure the effect of those ground wires. So that's one of the downsides to this. The thing is, when I was taking the measurements, basically the black wires weren't planned. I wasn't planning to add the extra ground wires. Those were sort of an afterthought that occurred to me after I added this one over here, because there's like this capacitor bank, and I was like, oh, maybe, I could like better physically affix it by adding some extra wires, because I didn't really want it to only be supported by the capacitor over here. And so I was like, okay, let's just hook it straight into the VRM, and we'll have some extra like current handling, like current carrying capacity by doing that. And then I was like, oh, well, let's do that everywhere a bit. And yeah, so I wasn't really planning to take ground, like I wasn't planning to have the ground connections, and so I was always measuring against the PCIe bracket, which is suboptimal. Ideally, what I would have been, like, the ideal way to take these measurements would have been to measure like the voltage across this capacitor, and then like the voltage from, well, it's actually really awkward in the VRM section. I guess you could have taken the voltage across the capacitor legs of the like bulk capacitors. you know, and that would give you like a really nice comparison measurement. But I really wanted a measurement. Well, I guess I could have also gone just like inductor to nearest capacitor leg, right? But yeah, I didn't do that because I was very lazy, and it's just awkward to do that kind of measurement with the card horizontal in the system while running Firestrike, right? The back of the card gets pretty hot, so you can't just like rest your hand against it and be like, oh yeah, I'm not gonna slip with the probe. It's like, you know what? Between taking accurate measurements and having a working card, and also being lazy, like technically I could have, you know, soldered wires on and then desoldered the. It's just like, but between, you know, being kind of lazy and wanting to keep the card alive, I didn't really take the best kinds of measurements that I could have. Either way, the measurements I did take are enough to show that my suspicion about the general shape of the power plane seems correct, and that most of the current does in fact do this, because the lowest voltage I measured was right here, right? That inductor was output, like the voltage at this inductor was just 1.129 volts. When the core was getting, you know, 1.073 volts. Meanwhile, the middle inductor, which you would kind of think, like, considering this layout of the VRM, right, like, it is this line, you would think that, like, and technically speaking, like, this inductor is, like, closest to the actual core, right? Like, the core is here, and if you look at the distance, like, you'd think this point right here should have the lowest voltage relative to the core, because it's closest. Nope, it doesn't. That's actually the highest voltage I measured. So really the power plane probably has some weird, like, sort of U-shaped thing going on. I'm really not sure why. Oh, I guess the PCIe interface hooks up over here. Right, yeah, because you'd need a bunch of, like, BGA in this area for the PCIe to connect to. So that makes a lot of sense, I guess, that, like, this actually ends up having the highest voltage, but anyway, it's not by much though, right? Like this point ended up at, what was it, 1.132 volts, whereas the bottom inductor, which this is actually, like, I was really expecting the bottom one to be at like 1.133 or like more. Like I was expecting the bottom one to be the highest voltage because it's the furthest away, and so there'd be the most voltage drop between that inductor and the actual GPU core, but there wasn't. So evidently there has to be some kind of connection that, you know, several layers down. Like, it's a multi-layer board. This is a GPU with GDDR6. It's probably 8 layers. Like, I really wouldn't be surprised if it's 8 layers, which is not actually that many for a GPU. It's actually very common for GPUs to be on, like, well, very high layer count PCBs compared to motherboards. Like, a motherboard having 8 layers is something relatively special. A GPU having 8 layers is kind of standard for anything. Well, for like GDDR5 cards, if it had a 384-bit bus, you're pretty much guaranteed that it's gonna have 8 layers, because there's just not many other ways to get a functioning GPU. But anyway, yeah, so this actually didn't have the highest voltage, like that bottom inductor, which is kind of interesting, and seems to indicate that some of the current seems to have some, like, there seems to be some connection over in this area that allows the current to sort of travel through to the, like, bottom edge of the core, but still, you know, most of the current evidently has to be doing this. Which makes a lot of sense if you look at also how a reference 3060 Ti PCB is laid out, as well as a lot of other, like, non-MSI 3060 Ti PCBs are laid out, where you'll actually have, like, 2 or 3 phases of power sort of in this area, which would basically connect into this, you know, V-core polygon that we have right here, and then you'd have, like, this really nice direct connection to the core, which, yeah, like, makes sense, right? Like, that's what we're seeing. Like, NVIDIA designed the core to take most of its power sort of through this corner. Actually, most of the connection would be right directly around here, but, like, it's pretty standard that a GPU will have, like, one corner where, like, the V-core power plane comes in, and then it spreads out into a blob under the actual chip itself. So, yeah, you'd probably have something like that in terms of, you know, how the current is supposed to flow. And so, yeah, that's, like, super, like, so that makes sense, and it's kind of weird that MSI opted for this, in a way, suboptimal VRM layout. Not that it's very, it's not really suboptimal. It's like a very minor difference. It's like 3 millivolts between, like, the optimal inductor position and the suboptimal, like, the least optimal inductor position, but it's still kind of interesting that, you know, like, we can measure that, and I wonder how other cards compare. Right, because this is admittedly one of, like, when I was buying this card, this was one of the cheapest 3060 Ti's I could get my hands on that was not made by, like, there was other 3060 Ti's, but as far as I could tell, those were on, like, 6-phase VRMs, and I'm not even like, my card has a 7-phase. I'm not very impressed by that. And so the idea of getting a card that was like, 10 quid cheaper or 20 quid cheaper and has one phase less was like, you know what? I'm just going to pay for the 20 quid extra. Also, the heatsink on the card is actually quite nice. So, I'm overall, like, I'm pretty happy with the card overall. It's just like, yeah. At the same time, I didn't have huge expectations because it was like one of the cheapest cards I could get. Anyway, so yeah, so that's sort of the voltage drops across the various inductors, or from the various inductors, and on average, the card in its stock configuration was losing about 58 millivolts of voltage between the V-Core VRM and the GPU core, and that's just on the current flowing from the VRM to the core, right? Again, because I was doing all of my measurements from the PCIe rear I/O bracket, I can't actually get you, like, I don't know what kind of, like, return, because, like, all of the current flows to the core and then back from the core into the VRM, right? Like, current does not flow in a, it's not one directional. It always goes in a loop. So it goes to the core and then it has to come back, and it makes its way back through, like, the ground plane of the GPU. And because of how I was taking my measurements, there's just no way for me to get the effect that the extra ground wires had. So all of this is just looking at the effect of the orange wires, and the black ones are, it's like, I have no idea what they actually did because I didn't measure that, because I didn't think I would be putting those black wires on the card until I already modified the card. So too late. Anyway, but yeah, so in the stock configuration, 58 millivolts voltage drop, and then after modifying the card by adding, what is it, like 4 wires? It is, yeah, it's literally just 4 wires. So 4 18 gauge, wires, the card now drops on average 45 millivolts, which is a small, insignificant, like, it is an improvement, but it's also total, like, it's insignificant. By my estimates, the card probably pulls around 165 amps at 1.073 volts, which, if you think about it, that's not really that much core power, but, like, there's other power rails on the card, and there's also the VRM power losses, so... which I was accounting for the VRM being like 90% efficient, which might be a little bit unrealistic because I guess I wasn't really accounting for the losses of the power plane itself in that calculation, but whatever, something around 165 amps. And the reason why I have to have this estimate is because you can't actually get a power reading from the V-Core VRM of an NVIDIA GPU, especially not this one. Well, actually, some cards you could, but this is not one of those cards, because... technically, the UP9512 voltage controller does support giving out power readings. The only issue is this VRM uses a bunch of DRMOS components. And DRMOS components have one major problem. They do not have like some crazy, like, they don't, like, unlike, say, smart power stages, they don't have like some accurate current monitoring system built into them. And so the current monitoring that's done for VRMs like this, is usually dependent either on low side MOSFET resistance, which is horribly inconsistent, or DC resistance of the inductors, which is also not really that consistent, because inductors, like, well, both the low side MOSFET resistance and the DC resistance of the inductors, they both go up and down based on operating temperature. All of the inductors in the VRM aren't going to be at exactly the same temperature at the same time. Same goes for the low side MOSFETs. They're not all going to be the same temperature. They're also not going to be the same exact value from the factory, because that's not actually, like, the low side MOSFET resistance isn't some super tightly controlled, variable. Same goes for the inductors. They're going to have a DCR of plus minus sort of whatever. And so so you end up in a situation where it's like technically this controller has a method of monitoring the current flowing through the VRM for the purposes of balancing the phases. And it does a perfectly good job of that. It's just not meant for actual, like, power monitoring in general, right? Like, this is not a great way to enforce, to get, like, a accurate power reading. And so, also getting a power reading from the controller is awkward as hell on NVIDIA cards. And so, yeah, I just have this sort of estimate of 165 amps based on how much the memory VRM seems to be pulling, how much power I think the V-Core VRM is losing, and, yeah, so not great, but... it should be pretty close. Anyway, so at this estimated 165 amps of current draw, The stock configuration of the power, like the stock card would be losing about 9.5 watts of power in the power plane. My card loses about 7. So an improvement of 2.145 watts, or basically, like, I'm sure if you found sensitive enough equipment, you could measure that the power plane on my card runs cooler. I don't think it would be by a very significant margin. Um, so, yeah. That's kind of that. So that's the Power Bridge mod, and this video turned out way longer than it was supposed to be. It's 20 minutes. I don't know how I keep doing this. There was an earlier take that was like 15 minutes. I didn't like it, and so I scrapped it, and so here we are. Now we have a 20-minute take. Oh, we did cover all the information I wanted to cover. So yeah, basically this, like, it didn't make the card worse in any way. I mean, it made it uglier, yes, but it didn't make it worse. Like, the card works, it runs just fine. All right, like, it's literally running my daily system daily. Um, and yeah, like, if I wanted to do this again, I think what I would do is just do it more, and I'd put more attention into this area. I think, like, a good idea would maybe be to just actually just scrape off the solder mask right here, and then scrape off the solder mask right there, or maybe even right here, and then just go, like, really nice thick connection right here. Right? Because that would be like a really short jump. Though I don't know if there's that much voltage loss in that specific area even to begin with. Like, that might actually not make much of a difference at all. And it would be much better to put a bunch of work into maybe, you know, like putting like twice as much copper into this connection or twice as much into this connection. Maybe also connecting like this tab and this tab, right? Like going like this, and, you know, yeah, like, eventually, I think you could probably get the card down to losing maybe 10, like, 30 millivolts, maybe less. But, yeah, in its default configuration, or in this configuration, I only got it down to lose about 45 millivolts on average, which just isn't that different from the 58 millivolts it started with. Like, it's an improvement. It's just not a very big one, and so it's not very impressive. And overall, and, like, I know why it's not impressive, because it's like, I didn't, like, they're 18 gauge wires. They're just not that thick. They're not going to make that much of a difference unless you're going to use like 10 of them. And there's not really that much space to work with here, right? So yeah, I only used 4. Like, I can see some, well, actually, like, this cap especially is annoying, right? Because there's just not much space to work in that area. Um, And actually, even this right here wouldn't really be that convenient to connect to. So that's kind of the main issue, is just like, maybe even doing something like this. Like, that might still be a, like, that could totally be a viable option. That would maybe work. Um, but yeah, at the same time, like, the card isn't losing tons of voltage to begin with, right? Like, 58 millivolts is not that much. I've seen far worse, but 50, so, you know, like, yeah, that's fine. So I'm overall happy with how the modification, like, yeah, ultimately I'm pretty happy with how the mod turned out. It runs, it's not very pretty, but you know, like, it's not like I have a, like, it's not like my daily system is focused on being pretty. Um, and the main thing is, like, card still works. The modification made a little bit of improvement. Um, now, like, now that I'm, like, criticizing this modification, I really feel like I should redo it. But the card lives in my daily, and I'm not pulling it out again. Like, I'm really happy to not be on an RX 580 anymore. So it's like, you know, yeah, I am, no. Like, I don't have yeah, no. If I had the opportunity to do this on another card, I would do it better. But since it's on my card, and that card is currently doing you know, just fine in my daily system, I'm not redoing this. Even though, like, yeah, it's not. It's pretty far from being the best that I could do. You know, even with my incredibly low standards, this is very far from the best that I could do. Um, Actually, maybe not that far, but, like, I'd say it's like halfway there. Maybe less than halfway there. So actually, that is pretty far. Anyway, that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, stickers, posters, hoodies. Speaking of hoodies, there's zipper hoodies. I highly recommend you check them out because, well, I personally like zipper hoodies. Pullover hoodies have always been just kind of like, I've never been a fan, but anyway, so there are now zipper hoodies on Teespring. And yeah, Patreon and Teespring allow me to do stupid stuff like this. So it would be much appreciated if you'd check them out, because, you know, yeah. Without you guys, I wouldn't be able to do stuff like this. Not that you should... Well, if you're doing this on like I wouldn't copy it if you're planning to put it in your daily system. Like, I do realize that I'm dailying this, but like, I think we can all agree that I have issues. Anyway, that's it for the video. Thanks for watching, and goodbye.